Thank you guys very much. Hey, Elizabeth. First of all, my great thanks to ACM and to everyone who put on this conference for inviting me, and to all of you. I really, really appreciate it. It's a great pleasure to be back here. So I graduated from here in 2001 in physics. And actually, it was in coming to this conference and conferences like this that really got me starting to think about computer science and about getting into computer science. It was at this point where I was doing physics, and if you want to do something new in physics, you really have to go through graduate school and be a postdoc and be a professor, and then eventually sort of make a Herculean effort and you can do something that is new. Not that necessarily that should be one's motivation in doing physics. There's just sort of the thrill of discovering things. But one of the things that really struck me is looking at someone who took an intro to AI class, and you see that they are able to build something that's hugely non-trivial, that solves a person's problem. And I was like, that's super cool. I want to do more of that. So what have I been doing since graduating? So I went and I got a master's in computer science at USC in Los Angeles. And I specialized in artificial intelligence, and I did a whole bunch of artificial intelligence research. So specifically in this field of AI, which is called multi-agent systems, which is essentially concerned about autonomous entities that sort of reason and act, and they want to do this in a coordinating way or sometimes in a competitive. So after doing that, I became a lecturer in computer science for a little while at USC. And then I was doing some applied research, and I was like, all right, this is okay, but I kind of want more out of life. I don't really know what that is exactly, though. And so I was debating between two things. I was thinking about getting a PhD in computer science in one hand, and on the other hand, I was offered the job of building the AI for Call of Duty, game Call of Duty. And I was like, which one of these things should I do? I ended up doing none of them. I started a startup instead. I did the thing that maximally displeased my parents. I did that, and then I worked at a couple of startups after that. And so today, I work in an AI lab at AT&T, this place called the AT&T Foundry, which is in Palo Alto, California, in the Bay Area. And so what do we do? So AT&T, like lots of big companies, finds itself in this really interesting situation, quote unquote interesting, in that it's a world of dramatically increasing scale and complexity and difficulty. And for 20, 25 plus years or longer, there have been all these problems where it's really been okay to address these manually. And they're these grizzled veterans who solve super complicated problems manually. But we're really reaching the scale where that is no longer feasible. And I will show some examples of that. But it's becoming really impossible. You can recognize the solution when someone sticks it in front of your face. But you're reaching the scale where there's a host of problems which we can no longer manually address them. And so me and my team, what we do is we build intelligent systems to manage that complexity. And I'm going to show a couple of examples during this talk. And in the course of doing this, we bring radical efficiency changes, so orders of magnitude. So things that used to take a month or longer will take an hour for one person, which used to take a team of people. Or things used to be impossible to do are now within the realm of possibility. Okay, so first, what are intelligent systems? What is this business all about? Why should anybody care? And then, what do we do with them at AT&T? So that's today. Okay, intelligent systems. So you use this word artificial intelligence and people freak out. So especially people outside of the technical community, you have experience talking about AI to your parents or to friends who aren't doing stuff in technology. You use the word artificial intelligence and the thing that immediately pops into their head is Terminator and artificially intelligent human beings, or synthetic human beings. And so personally, I try not to use this word, artificial intelligence. I instead use a much less loaded word, intelligent systems. And so what do we mean by this? So let's suppose I give you a list of unordered numbers. And we want something where you hand this list of unordered numbers to a box, and it produces that same list, but in an ordered sequence. And so this thing that accomplishes this task, can we say that this is an intelligent system? So all of us who know things about computer science, we would like to say, no, this is not an intelligent system. And sort of like our intuition is like, it doesn't feel right. I don't think it is. Now, why is that? It's because people who have studied computer science know that we have algorithms like quicksort and bucket sort that have provably optimal properties. That if you run them on a list of numbers, it'll give you like the optimal list of steps to put these numbers in sorted order, and like there for various assumptions is the best method in order to put them into sorted order. And if you have the optimal solution, you should use it. So here's the thing. Let's suppose that I didn't know anything about computer science. I was just some dude, haven't read anything about computer science. What I do know, however, is I know how to swap two numbers. And if someone showed me the right answer, I would be able to tell you, yes, this is in fact the right answer. I could recognize it. How far can I get just with that? So what you could do is you could start with the initial configuration of numbers. And I might make a guess. Okay, here are two different ways in which I can make my first swap. From each one of those possible hypothetical futures, you could continue making, oh, that sounds so good. You can continue making, whatever, it's fine. You can continue making guesses as to how to swap until eventually you arrive at a point where the numbers are in the desired configuration. And if you simply follow this path from the leaf to the node, you get a list of steps that puts the numbers in sorted order, and with a very small number of assumptions, actually produces a list of steps that is just as optimal as would have come out of something like quicksort or bucket sort. And so who cares? Like, I was able to use search, and I was able to reproduce the same steps that would have come out of quicksort, even though I don't know anything about comparative search algorithms, which is okay. That's kind of cool. But here's the thing: the very same algorithm, with very, very, very minimal changes, does things like theorem proving. So this is a page from Chapter 2 of Principia Mathematica by Russell and Whitehead, and a theorem proving system was able to reproduce the proofs for all of the theorems in Chapter 2, and some of the time was able to produce proofs that were shorter than those that appear in the book. The very same algorithm, essentially unchanged, is used to do things like military logistics planning. So this is a thing where I got a bunch of stuff in military base A, and I want to move it to military base B. So like crates of oranges and stuff like that. And the way that this used to work is people would sit for months and they would manually think of a plan that is tens of thousands of steps long, and it involves things like take this crate off of this truck, and these people have to be present when that happens, and then put it on this van, and then drive this van to this dock and put these things on this boat. And it's like this massive, tremendously difficult logistical problem that took people months to solve. So the military engaged instead with researchers who built planning-based systems that solved the very same problem in hours. And so here's the big idea. Quicksort is really good, and it is the optimal answer for some cases, but it only sorts numbers. This super simple AI algorithm, which many of you will recognize as search, guided search, solves a tremendously large list of problems, including sorting numbers. And so that's great. Using this simple algorithm, I was able to reproduce this knowledge. But you know, I could have done this with just like a small amount of reading. If I just like read a couple of papers or read CLR, I could have solved this problem. Some of you may recognize this photo. So this is an image of Lee Sedol losing. So he at the time was the world's #1 champion Go player, losing to AlphaGo, which is a software created by Dini. So for those of you who are unfamiliar, Go is a game which is many thousands of years old, and it's super complex. So much so that there has been this standing challenge for someone to make a piece of software to defeat a professionally ranked Go player. And this challenge had gone unanswered. There's prize money attached to this challenge of $1 million. It had gone unanswered for decades, until this year, in which DeepMind created a system that defeated a professionally ranked player, in this case, the world's best Go player, for the first time ever. It was a huge, huge, huge deal, a tremendous achievement. But the thing is, human beings know how to play Go, right? Like if you give them a game, they know what to do. Lee Sedol knows what to do. But the problem is it takes a lifetime of dedication in order to arrive at this knowledge. And the people who made AlphaGo, like they know a couple of things about Go, but they're not experts. Like they don't really know how to play. So instead, what they did is they found a way to describe the nature of the game to AlphaGo, and then AlphaGo told them what the solution was, and reproduced this knowledge. And in fact, it produced novel strategies for playing this game that have never been seen in the entire history that the game has been played. And those strategies that have been discovered have since been employed by professional players to play against other human players. So super interesting. So where this becomes really interesting, so that was an example where AI was being used to reproduce knowledge that was simply hard to come by. It becomes really interesting when it is used to produce knowledge that nobody knows. Nobody knows what the solution is. So if I were to give you a picture of a face, pretty much everyone in this room, hopefully, would be able to instantly determine, yes, this is a face, this is not a face. But if I were to ask you to write down a sequence of steps that unambiguously said, okay, when I give you this input of a face, you do this, you do this, you do this, you do this, and yes, this is certainly a face, or this is not a face. This is knowledge that essentially we have access to intuitively. We only have access to this on a totally subconscious level. No one really can express how to solve that problem. So instead, what you can do is you give many examples of this is a face, this is not a face, to a machine learning system, and then it is able to whittle out the generality from these images. And then it can produce an unambiguous list of steps, where if you execute this list of steps, it will tell us this is a face and this is not a face. So in general, the way to think about intelligent systems and AI, in my opinion, is as a general problem-solving tool, a bag of problem-solving tools. That there's a problem that you want to solve, and if you know what the solution is, you should use the solution, and you can write a program that simply executes that solution. But the issue is that if nobody knows what the solution is, or the solution is very hard to enumerate, instead, you can simply take the problem statement and give it to an intelligent system, and then it will tell you what the solution is. However, I really want to emphasize that pretty much wherever you go, if you have some problem, people care about this problem. And so there have been a body of people who have been paying attention to this problem, and maybe they have an optimal answer. And if there's an optimal answer, you should use it. So a really great example is things like examining a CAT scan and trying to diagnose something from this. So there's a field of experts who perform this task. They're doctors. And they're really good at this because they trained and studied this problem for a really long time. But even then, there are a set of problems which even they are unable to produce solutions. And in those cases, we have intelligent systems that aid them. Okay. So to do this, people typically build two features which human beings pretty much take for granted. So the first is the ability to represent knowledge with probabilistic systems. So back in the day, people used logic-based systems in order to accomplish this. So they came up with simple logic-based rules to describe features of the world. So the problem is that these were super brittle and really lacked any kind of expressiveness to describe anything remotely realistic. So for example, if you wanted to come up with a rule that described if something flies or not, you could be like, okay, well, if it's a bird, it flies. Well, okay, what if it's a penguin? Okay, if it's a bird but it's not a penguin, then it flies. Okay, what if its feet are stuck in tar? Okay, if it's a bird and it's not a penguin and its feet aren't stuck in tar, then it flies. And there's this infinitely long list of exceptions. You will never get to all of them. It's really not a good way, in general, to capture realistic systems. So this is this triumph of machine learning and all of the sort of wealth of knowledge that people have developed to describe probabilistic systems. It allows you to do things like combine multiple independent observations to inform the degree to which you believe something is true. So super, super powerful. Secondly, we need the ability to reason about long-term goals. So if I'm playing chess, for example, the thing that I do now influences the state of the game 20 moves in the future. Or, more pertinent to the situation, if today I am an engineering student and I want a career as a computer scientist or something like that, there's a long list of steps that one must perform in order to get from here to there. And the outcome of any of these actions are totally non-deterministic, but in the face of this, and I have not exactly a super well-formed goal, and in the face of this, how do I act? How do I act over long term in order to make things that I want to happen happen? So people put these two things together, and they make miraculous things happen. So in general, when we think about what do we want to tackle, what sort of problem do we want to solve, we look for a couple of things. So you want a problem that is increasing in scale and complexity. So it used to be something where people could address it manually, but now the problem is simply way too complicated. You can't fit it in your brain. You can't even, not only can you not fit it in your brain, but one cannot even enumerate what the steps of a solution are. Secondly, they can recognize a solution when they see it. So if you've got these two things, this is the recipe for being able to apply an intelligent system and get a really tremendous win. So today, okay, so I want to talk about a couple of examples of how we did this at AT&T to make a big difference. So, example number one, diagnostic systems. Okay, so when you think about AT&T, like what's one of the first things that come to mind? Well, essentially one of its greatest assets is this giant physical network. So it's this giant network, spans the entire nation, comprised of millions of machines, with things like cell towers and routers and switches and things flow on this network. So things like mobile phone information and like cable television data, and as well as voice data. And this is a machine which has essentially been in continuous operation for 100 years, constantly being maintained, improved, upgraded, which is really like amazing. It's an amazing feat of engineering if you think about it. And so let's think about a simple connection. So I've got 2 points, A and Z. It's called A and Z for historical reasons, God knows why. But let's suppose I've got points A and Z connected by a wire, and there are people at points A and Z, and they can talk to each other. But the thing is that it's some like super ultra high capacity link, and just having one conversation happen on this link is like, it seems kind of wasteful. What you'd like is for 2 sets of people to be able to talk to each other. So A1 and Z1 should be able to talk to each other, A2, Z2 should be able to talk to each other. And they should be able to do it in a way where essentially they're like oblivious of each other. Like they shouldn't have to care that there's a second person who is they're sharing this with. And so how is this accomplished? Well, a simple way to describe how people solve this is something called multiplexing. So let's suppose on the link between A and Z, I've just got like some jumble of words that are going down there. And A1 and Z1, they have this agreement. They're like, all right, every even word is for us. And then A2, Z2 says, all right, we get every odd word. And so if someone were just to sample words coming off of the link between A and Z, it just sounds like gibberish, right? It sounds like a bunch of words that are mixed together which don't make any sense. However, A1 and Z1, they know how to use this, right? They say, all right, I'm going to take every other word, and this forms our conversation. And then A2 and Z2 do the same thing. And you can imagine that they might construct a device that automatically gets the right word. And doing this, they can each have a conversation, totally oblivious of the other person. They don't have to care that they're using the same physical wire. And in this way, you have a physical connection that supports 2 logical connections. We say that A1, Z1, A2, Z2 are one level up in the hierarchy, what they call the multiplexing hierarchy. And so it's not exactly like this is kind of a simplification. And so you can imagine that now that A1, Z1, A2, Z2 have their own connections, they don't have to worry about anybody else, they might even decide to split it up even further into higher levels of the hierarchy. So A1 say, you know what, I want, even though I've got every other word, I'm going to let, of that stream, I'm going to let some other person use every other word of that stream. And so A11 and Z11, for example, now they get like every 4th word that goes on between A and Z. And so in this way, you can imagine levels of a hierarchy of information. So A11, Z11, they have a channel of communication, a logical channel, which uses A1, Z1, which then uses the physical connection, A. And so you can imagine that if something happens on level 1, it has an impact on what happens in level 3, right? So if level 3 says, hey, something's wrong, maybe something's wrong on at a lower level that has influenced that. And so you can imagine, so in order to measure that, what we do is we look at the machines that operate on each level, and they're just emitting events that are essentially status events. They say like, all right, here's how I'm doing. So simple example, let's suppose you cut the physical layer, so level 1. So like with a lawnmower, you cut like a fiber optic cable. So like it stands to reason that everything that rides that will no longer function. And in fact, the machines A and Z, when that happens, they're programmed to emit specific phrases. So in this case, they emit something like loss of signal. And so if A11, Z11, where like UVerse is traveling, for example, they say like, hey, I got a problem with my connection. And the technician says, all right, I'm going to go to level 1, and they see this phrase being emitted, loss of signal. They're like, okay, I know what's wrong. Fiber is cut. We should go do something about it. The problem is when the symptom is something much more high level. It's some sort of more phenomenological thing, something like slow connection, something for which there are many thousands of possible independent causes that might independently contribute to slow connection happening. So when that happens, what should I do? How do I find the cause of the problem? So to answer that, let's think about how the problem is manually addressed today. So what happens? So these are examples of messages that are emitted on the level 1 level. So what happens is you have some symptom. So in this, we call it a ticket, slow connection. And a technician goes in there, examines log messages, and they apply their intuition and experience and their knowledge, and they say, okay, this line, this line, this line, I think this has something to do with what is wrong. And I'm going to select these lines. They seem to be most pertinent, and I'll use them to compile a report. But the problem is this does not scale. There's a fire hose of this information that's just constantly being emitted. There are teams of people. They scour through terabytes of data. It's doing this problem, essentially, applying their intuition, their knowledge, their experience, trying to find which lines are relevant, which ones are not. And what we want to do is we just want to reduce this fire hose. We want so at any given time, most of this fire hose of data is not relevant to the problem. But like you don't know which one is which. So what we want to do is build systems that find the part of this fire hose that is relevant. And then show that to the technician, just sort of bring that to the attention of the technician. And the thing is that if you ask the technician, hey, give me a set of steps by which I can identify what lines are important, and I'll just put that in a program and just select them for you. The answer is, I don't know. I don't know what they are, because it's totally from their intuition and their experience. It's not something that they can capture in an algorithm. And in addition to that, there are problems for which technicians cannot diagnose. It's simply too complex of a problem. They cannot sort out how to identify what the root cause of the problem is. And so these are all the recipes, these are all the criteria that we are looking for the application of an intelligent system. And so let's examine, what would an intelligent system approach mean? Okay, so essentially what we're trying to do, we want to look at places where the slow connection symptom is happening. And then during that active period, what are events that are being emitted by the machines at the different levels? We want to look at lots and lots of those examples. And essentially the question is, what is different about these events when slow connection is active versus not active? So we've got plenty of examples of that. The problem is, if you look at, for example, just a state, there are hundreds of thousands of these machines. All these events are being emitted. They're all being aggregated into this massive feed. Slow connection never happens by itself. In fact, at any given time, there are thousands or tens of thousands of other events which are also occurring. All of them can be having an impact on the very same list of events. And so if you see a change in the content of one of these events, it's really hard to say that this change was due to slow connection, or was it due to one of the tens of thousands of other things which were happening at the same time. So the problem is, how do we isolate the impact of just this one thing, slow connection? So if you examine this problem from the point of view of like medicine or like epidemiology, for example, they describe it in terms of something called confounding variables. So some of you may be familiar with this business. And so the idea is, what do? We want to keep the variable that we're interested in fixed, and we randomize for the presence of the other ones. And so the idea is we want to collect a bunch of training samples that represent the other variables going all over the place, like every possible configuration that they might take on. I want lots of data describing that while holding this one thing fixed. The problem is that's not really feasible here, because there are tens of thousands of other variables. You really can't collect data in order to randomize for all of them. So is there some way in which we can reduce the set of variables? So like, what are we trying to do? Okay, so in this table, as you're going down the table, these are segments of time. And so at any given time, moment in time, we look at what are the tickets which are active, which ones are not active. So you can see, okay, at time 1, slow connection is not active, but the other tickets are active. At time 2, slow connection is active, but the other ones are or aren't, and so on. And so the idea is you want to fix slow connection at 1, for example, at active. And you want to find examples of training data that cover every possible other way in which the other tens of thousands of tickets might take on. But you don't want to do this with 9,999 other variables. Can we do it with a fewer number? So if you have studied statistics, there's a standard answer to this problem, which is something called principal component analysis, which you may be familiar with. That doesn't work in this situation. There are lots of assumptions in principal component analysis, specifically that there's a linear relationship between your variables. That is not the case here. And so instead, we use a more general concept, something called Bayesian belief networks. They also go by the moniker of probabilistic graphs, or just Bayesian networks. And essentially what they do is they capture what's called conditional independence relationships. The idea is that if I've got a variable I'm interested in, slow connection, the idea is what are other variables which tend to have a direct or indirect relationship with slow connection? So this tells me if slow connection happens, what's other stuff which also tends to be there or tends to not be there? Everything else, everything outside of that sphere, is basically just random stuff that comes and goes. And if I just collect enough data, I will just average out the effects of all of those things. But this collection of stuff that's related to slow connection, that won't be averaged out. That's always tends to be there when slow connection is there. And so using this technique, we're able to find the variables that matter. And in fact, we were able to reduce the set of tens of thousands of variables to like a dozen that turn out matter. And so we then randomize just for those. And so what the outcome of this really is just a set of training examples that maximally illustrates the impact of slow connection. And then when we do that, we apply deep learning models that really make an impact. So really, the thing that deep learning methods are really good at is feature selection. So they tell you essentially what is it about your data that is important to look at. And that's precisely what we're looking at here. So if we were to make like a hypothesis about like what n grams of words we're supposed to be looking for in the log data, it would be like, we won't get very far. What we want deep learning systems to examine the data and tell us what collections of words are important. And so that's exactly what they do. And then in fact, when we look at frequency distributions of these words, we can see that, okay, when slow connection is active versus not active, these are in fact different distributions. And then we use those phrases, we look for the appearance of those phrases, and then we use that to score lines appearing in a log file. And then in doing this, we automate the process of coming up with these reports. And so just like that, something that was 12 plus hours or a multi-day effort for a team of people scouring through terabytes of data now takes an hour. So this is an example of what I mean. You can use intelligent systems to take something which was previously inscrutable, which took an immense amount of manual labor, and you make a radical efficiency change. And this is just the beginning. We want to do lots and lots of things building upon this. One of the things which is really interesting is we want to take knowledge which is extracted by the system and use it to inform books of good practice, essentially knowledge that can be transferred to technicians operating the machine. So that's diagnostic systems. There's one other problem that I wanted to talk about, intelligent infrastructure. So I think this is super cool. So as an example, let's think about the DNS service. So I'm sure everybody in this room knows all about DNS. So it's simply, I give you a domain name. I want the IP address in exchange for that. So you can imagine any service instead of DNS. DNS is just an example. But the thing is that when you sell a service to somebody, if you're some company selling something as a service, you have something called an SLA, or a service level agreement, that are in contracts. And what this says is, okay, I'm going to sell you this service, and I'm going to guarantee that 85% of the time, the response is going to be returned to you within 35 milliseconds or less. And so this is just a CDF which just illustrates that. But this is, like, seriously, this is stuff that goes into contracts, and people take this very seriously. The problem is, no one really knows how to make this happen. What they do instead is they just massively over-provision, right? So they say, okay, I'm going to jack up my number of virtual machine instances in order to meet my desired response time. And like, you know, just to be safe, let's just like max out our credit cards. We'll get all the instances that we possibly can. And if anyone has experience using AWS, you see they have rules in there, right? That are things like, and you recall earlier in the talk, we talked about all the problems that are inherent in using rules in order to do stuff. If the average CPU utilization is greater than 80%, then jack up the number of instances by some number, and then if it falls below some threshold, we can decrement it by something. But this is the current industry practice. It's basically prayer. So we want to do better. But the problem is, it's hard. Like, you know, they don't like want to just resort to praying. Like, they want to do the right thing, but nobody really knows what that is. And so this motivates an intelligent systems approach. So the problem is, like, all right, my average response time is kind of crappy, and I want it to go down. And so to do that, I want to increase my number of instances. But the thing is that doing that comes at a cost. Using things like AWS is expensive. And so if I increase my number of instances, it's going to cost me more money. So I have these conflicting objectives. And so what should I do about this? How do I reason about this problem? So the answer is something called decision theory. So I'm just going to say, for those of you who are in the Mechmania competition, you may want to pay extra close attention. I'm just saying. You didn't hear that from me. This is really formalized with something called Markov decision processes. So essentially, MDPs are a way to reason about acting over time in worlds where the impact of actions are non-deterministic. So you do something and like you don't know exactly where you're going to end up. And secondly, you have very complex objective functions. So in situations just like this where you have multiple conflicting objectives, how do I reason about what I'm supposed to do? So one of the places in which this was developed, for example, one is economics and economics theory, but also robotics. So things like, if any of you have had any experience building robots, you know when you give it the command, I want you to go pick up that apple, sometimes it succeeds, right? It's not a deterministic process. It's not like, if you give it the command, I want you to rotate your arm by this many degrees, it's not going to go exactly that many degrees. It'll go approximately there, and there's a distribution that describes exactly where it's going to end up. So the problem is, like, how do I reason about making the long-term things happen, given that every step along the way, there's uncertainty that is involved? And so MDPs are all about that. So what do I do? So I got a set of states that make up my world. So wherever I am in this world, I'm going to be in one of these states. And then in some state, SI, I'm going to commit some action A, and I'm going to, when I do this action A, I'm going to end up in one of these possible future states according to some probability. So to make this concrete, in our example of a auto-scaling pool, let's say our state is the number of instances that we presently have, and what's our current average response time. So one slow, one normal, one fast, all the way up to 5 fast. So there are 15 total states in this state space. From a given state, I can take one of 3 actions. I can increase my number of instances, I can decrease it, or I can do nothing. And if I take one of these actions, I'm going to end up in one of the other states with some probability. So can someone think about why this might not be deterministic? So like if I have a certain number of instances and I say, give me another instance, Amazon, like why might it not be totally deterministic? Okay, it's okay. So lots of reasons. So first of all, Amazon is not exactly 100% reliable. I understand I'm being live streamed right now. It's okay. In the sense that if you say, hey, give me an instance, like it doesn't immediately give you an instance, right? Like sometimes it gives it to you immediately. Sometimes it takes like a couple of minutes. So like you don't know exactly when you're going to get the new instance. And so there's uncertainty as to what happens at the next time step. Secondly, there's uncertainty involved in what the rest of the world is doing, right? You're swimming in this soup of incoming requests that are constantly coming in. And so if you were in the state of like too slow, and you say, okay, I want to increase my number of instances to get to 3 fast, you might not get to 3 fast because in the meantime, the number of requests that you may have been receiving has jacked up. And so now you're still going to be slow. 3 instances isn't going to be enough. Okay, we need one more thing, which is preference, right? We have an agenda. We care about what happens in this world. And so it's made of these two conflicting things. I'm in some state, I take an action, and I want to be rewarded for matching the demand. So if I have 3 instances and it's slow, I want to be rewarded for giving the command increase the number of instances. And if it's 3 but it's fast, I want to be rewarded for decreasing the number of instances because I didn't need that many. At the same time, you want to be penalized, or you want to reflect the cost of running a number of instances. So that's what makes up your reward. And so you get these 4 things. That's what makes up your framework. You've got the set of states, one of the 15 states you might find yourself in. At any state, I can increase or decrease the number of instances that I have, or I can choose to do nothing. For a state, I commit an action, and there's a probability with which I'll end up in a future state. And then if I'm in a state, I care about which action that I will do. There's a reward for this, right? Okay, so once I've got this, what do I want? I want a policy which tells me how to get a lot of reward in this world. So if I'm in some state, what action should I do in that state such that in the long term it will be good for me? I will accumulate a lot of reward. So you can imagine if you just pick some random policy, that's some mapping from state to action, and let's just follow this. So you start in the initial state too slow. And I ask my policy, what should I do here? Should I increase my number of instances? Should I decrease it? Should I do nothing? And you follow that action. The result is you end up in some new state, 3 slow. So you said, okay, I want to increase my number of instances. I end up in 3 slow. And then for my trouble, I picked up some reward. And then you ask the oracle again, which action should I do? It gives you an action. And then you continue in this manner, continue acting over a period of time until ultimately you say, I'm in for it fast. You can continue acting or not. And so there's this question of, what was the value, how good was this policy? So if I have this policy and I started in the state too slow, how good was it to do this? So the way that we evaluate this is we sum the rewards along the way, and we discount it by some factor of gamma, because we want to prioritize stuff happening sooner than later. So we say the value of being in too slow and following this policy is the sum of rewards discounted by this factor. But the thing is that it's probabilistic, right? So like you're sampling from your distribution, and you're not sure exactly which state you're going to end up in. So you want to average over this. You want to do many runs of this, like hundreds, thousands of runs, and you want to take the average of that. And so that average is the value of following a policy in that state. And you can imagine if you mess with the policy pi, that will change the long-run value that you're able to pick up along the way. And so it stands to reason that there is a policy pi, which is the best policy. That for every given state will give you the most amount of value that you can expect to pick up by continuing to act indefinitely. And so let's apply it to this situation. So on the right, you see each of the possible 15 states that you might start from. And at the top is just a reminder about what constituted a reward, right? So the reward is constituted of changing my number of instances to sort of meet the demand. And then secondly, the cost for running. And so in this case, this graph depicts the cost of running is 0. So let's suppose that we just care about ratcheting up the number of instances or down in order to meet the demand. And so the right is essentially this algorithm that's running, and it's trying to settle upon how good is this policy. So when it reaches a line, it has come to the knowledge of here's how good, here's how much reward I stand to gain as I start from this initial state, and then I continue acting in the future. And so there's a line for each state, but you can see it converges to one of these 3 lines. So essentially, this is falls back to a feedback control system. So if I start from a state of like 1 fast, there's lots of reward to be gained. So basically, as like demand comes in, I can continue to ratchet up my instances to get to a state where everything is great. Or it can be a state where like maybe I start at like 3 like fast and everything is fine. I don't have to do anything. In which case, you don't pick up any reward because there's no action. So it resolves itself to essentially feedback control. Now it becomes interesting when the cost of running starts to come into play. So instead of being 0, now there's a cost to having a number of instances. So you can see that now it matters which state you start in. So if I start in some state, it impacts the amount of reward that I stand to get as I continue to go on. And where this becomes really interesting is when the cost of running becomes slightly higher. So the thing to look at this, so it was cut off a little bit from the graph, but I'll just point it out. So if you look closely at the graph, you will see that it turns out there is a higher long-term reward that you get in staying at 4 than for any of the 5 states. So if you're in 4 slow, so you have 4 instances running, you could increase your number of instances by 1. And you're being inundated with requests, So you're experiencing a slow average response time. And so you're thinking to yourself, like, oh man, like, I have a little bit of money, maybe I should use some of it in order to increase my number of instances. You can show quantitatively that if you do that, it is not worth it in the long term. It's actually better to stay in 4 slow. And so this is a super simple example about how AI can be used to help human operators make hard decisions. So there are lots of situations in which a human being is basically in a super high stress situation, and they're basically just trying to eyeball it. And most of the time, they probably would make the wrong decision. Be like, you know what, I really just care about page views and about having fast page views right now, so I'll just go ahead and eat the additional money and have another instance. So in general, in problems that we face, they're much larger in size, so like many times more states, much larger action space. States aren't even fully observable. You just sort of have observations which inform your idea about what your state in. You have like teams of agents that are acting together instead of this is just like one single machine trying to act on its own. So, the thing that I'm trying to say in general is the way to think about AI is as a general set of problem-solving tools. And in general, if you have an optimal answer, you should use the optimal answer. But you know, in cases where the problem is starting to become really complex, it's really becoming too hard to fit it in your mind, and not only can it not be solved manually, but you can't even enumerate what are the steps. You couldn't even write a program to execute the solution to this problem. Those are the places where an intelligent system is motivated. And if you find situations like that, you can make something that has a gigantic impact upon how your business or your institution or a problem operates. So, we can't do this alone. As I mentioned, AT&T is in this world of increasing scale and difficulty and complexity, and we're in the process of building intelligent systems to address all of these things. And so if you're interested in getting involved in AI on a massive scale, and you want to work on problems that pretty much nobody else is working on outside of academia, then AT&T at the Foundry is a really good place to do it. So we write papers, we contribute open source software, we also write patents from time to time, but most importantly, we build systems. We build real live systems that solve people's problems and save millions and millions of dollars. And so if you find this interesting, please come and talk to me, or write me, or reach me on Twitter, or just come and grab me. I'll be around all day. I'll probably be around tomorrow morning as well. And that's all I had. Thank you very much for listening. So if anyone has any questions, I'd be very happy to answer your questions. Yes, sir.
Could you actually scroll back to the state definition of the whole Amazon data? That one. And one more to policies. Oh.
This one?
No, you had it right. There was the pod policy definition. Yes, that one.
I can recommend some really good references if you're interested. Cool. All right. Thanks very much, guys.